My name is Alex from Team Magmo, and I'm here to talk about moving at the speed of Nitro, use case for Testground. That was my attempt at a clever title to talk about the Testground testing tool and some of the benefits we've gotten from it. I'll start off with a brief outline. So I'm going to give a brief overview of our Go Nitro framework. It'll be similar to what George covered, with some slightly different diagrams, maybe a few added mistakes. I'll talk about the Testground testing tool and framework and how we use it. I'll talk about some of the metrics we capture from our Testground tests, and we'll do a little bit of a performance investigation into it. I'll chat a little bit about how we can mock different network conditions and how that affects our metrics. And I'll talk a little bit about how we're trying to contribute back to the Testground project and what's next for Testground and Go Nitro, and then I'll leave some time for questions at the end. Okay, so how does Go Nitro work? So basically, retrieval clients and providers open a directly funded channel with the hub. I think you saw that in George's presentation. So you can see here, they have a directly funded channel with the hub. They do this by calling a smart contract a deposit method, which locks up their funds on-chain. Once this is done, clients can open virtual payment channels with providers. It's going to be done completely off-chain. So you see here, and then once that channel is open, clients can use it to send payments to the provider. Eventually, the client and provider are going to close that virtual channel, and the ledger channel gets updated with the balances. And then when the provider wants to withdraw their funds, they'll have to call into the contract, call the withdrawal method on the contract. Measuring the speed of state channels. Basically, we were looking for a tool to measure performance of our state channel framework. When we first started looking, we found a lot of tools that were performance tools that were designed around the server-client model, but not that much for like the peer-to-peer distributed world. However, lucky for us, Protocol Labs has already struggled with this problem and built a really awesome tool called Testground, which is a testing framework designed for like testing and benchmarking your distributed or your peer-to-peer system. And it was originally designed to test and measure IPFS and the libp2p code bases. So what is Testground? Basically, Testground is a platform for testing, benchmarking, and simulating complicated distributed or peer-to-peer systems. It lets you write code that gets spun up in a configurable amount of instances. It handles all the hard work of spinning up those instances, and also provides an API that allows those instances to coordinate and figure out what role they're going to play in a test. And it also provides a lot of infrastructure to record performance metrics and then report on that, which is super handy. So how does Testground work? It runs as a daemon listening for test requests. You can either have it running locally or, like we have, it running on a cloud VM. When it receives a request, it builds your test code. It runs the code in a configurable amount of Docker instances. I have a little star there because you can also not use Docker, but that's just the way we do it. It handles cleaning up after your test is done, and it writes out any metrics you captured to a database. It also exposes a nice web UI here where you can check the status of your test runs, see if they've succeeded, and it has links to logs and some artifacts. So how do we use it? Well, we've written a test case for Testground that uses our Go Nitro client to make payments. That's just written in Go. Messaging between instances is handled with a libp2p messaging service using the TCP transport. Like I said, we run the Testground daemon on a cloud VM, so that way we can all share results between the team. On that Testground VM, we also have a Docker instance running Hardhat that serves as our blockchain. And we use the metrics API that Testground provides to record a bunch of metrics. And I just want to point out that Testground also serves as our main integration test. So what happens in our tests? So basically, our Go Nitro test has a configurable amount of like clients, hubs, providers. You basically can specify what you want the network to look like. The first thing that happens is everyone opens a funded ledger channel with the hub. It's not shown in this diagram, but that just lets you spin up virtual channels in the future. Once that's done, clients start selecting random providers using a random hub. They open a payment channel. As you can see here, they send a few payments on that payment channel, and then they close it. And then we repeat this for the duration of the test. So what does that look like? I have a little GIF here of it running. So we put in the command, you can see it building, see it spinning up Docker instances, and payments start coming through. And you can see payments are being sent between different providers and clients. Another really cool thing is that we've integrated this into our CI. So whenever we create a pull request, we actually trigger a Testground run. Once that run completes, we add our CI adds a comment to the pull request. And on that comment, we have a lot of neat things. Like we have links to some performance dashboards. We have a link to logs and links to some build artifacts there. And this is really great because it lets us make a change and measure the performance impact of that change almost immediately. I think it takes our scenario takes maybe 2 minutes to run, so it's a really quick and nice feedback loop. So measuring performance, how do we do that with Testground? Well, Testground provides a metrics API. It's based on Go metrics. Any of the metrics you do record get recorded to a database that Testground is responsible for spinning up. It also spins up a Grafana Docker instance. This just lets you easily create dashboards against it. And we use dependency injection so we can into our Go Nitro client. So the Go Nitro client itself can record metrics. What do we want to measure? Our main benchmark so far has been time to first payment. That's basically the time it takes to open a virtual channel and send a payment on that channel. The reason we want to look at this is, one, it places the largest load on the hub or intermediaries in the system. Once the virtual channels are open and payments are being sent through, the hub is not even involved. And a quick time to first payment is really important for user experience in a minimal trust world, because you don't want to start providing service until you receive a payment. So before I jump into metrics, I'm just going to give a quick overview of the scenario that I'm using under the covers. Basically, we have 8 participants, so it'll be 8 Docker instances. 2 of them will be clients or payers. 1 will serve as the hub or intermediary, and then we'll have 5 payees or retrieval providers. The duration is just 60 seconds, and each payer will try to maintain 3 open virtual channels for the duration of the test. So they'll be constantly opening channels, sending payments, closing them, and opening them again, so that we're always maintaining 3 open virtual channels. I'll get into this a bit more, but we also mimic some network conditions. Right now, our scenario uses 10 milliseconds latency and 1 millisecond network jitter. So yeah, what does the result look like? This is our time to first payment dashboard that we've created in Grafana, and this is just a run we've done. So yeah, on the very top here, we just have some nice details. We have the unique Testground run ID. For every Testground run, you get a nice unique ID. Got some version information, and then just a breakdown of what roles different instances are playing, and the latency information. You can see here, right now, our time to first payment is 110 milliseconds, which is slightly above the number George gave, but we'll get into that a bit more. Down here, we just have it broken down by client. And we can also notice there's a bit of a large spike here, so we'll kind of look into that a bit more too. Another thing we can look at is payment throughput. I guess there's 2 caveats here right now. This is just measuring payments dispatched. Like in the real world, the retrieval providers need to verify the payments. And the other thing is we've designed our test scenario around testing time to first payment. So we open a virtual channel, send a couple payments, and then close it. So you get numbers that aren't that impressive. However, if you start sending more payments on one virtual channel, in this example, we're sending 100 payments on a virtual channel. You see you can get some much nicer numbers there. So now I'm going to just go through a little bit of a performance investigation with you guys. So one important part of performance is obviously messaging. It's going to play a huge role in your system. And just with the way our code is written now, we actually block on sending a message. So I was kind of curious, how long does that take, and like, what's the impact on performance there? So the really awesome thing about Testground is that it's really easy to like figure this out. So on the bottom left there, we have this little helper function in our Go Nitro client library. Basically, you can just drop that into a function and commit that, and that's going to start recording the function duration metrics as soon as that's committed. And then once that's done, we can easily just create a nice dashboard, you can see here, to kind of look at what's happening. So why don't we look at that in a bit more detail. So you can see here, this is the duration to send a message, the average duration. So it spikes at the beginning. There's a bit of plateau where there's a pause in the test, and then it spikes up again. So these numbers aren't awful, but they're certainly significant. So what if we didn't block on sending a message? What if we just made a simple change to use a Go routine to send messages? How would that affect performance? Well, we tried that, and all it took was making that one change and pushing it up, and we could see on our CI within 2 to 3 minutes, it definitely helped. So now we're under 100 milliseconds, and we also don't have as nasty a spike at the start, which is great. Another thing I want to just touch on is that we support multi-hop payments in our Testground tests. George talked about this a little, but it's been great because we've been able to, we accept you can specify the amount of intermediaries in the multi-hop test, and I think it really demonstrates the power of Testground, because we went from wondering if this is possible, to calling, implementing it, to verifying it with the Testground test within days. And what's the multi-hop result look like? So not as impressive. We haven't done too much work really investigating or looking at the multi-hop stuff yet. I think the really important thing for us is that it doesn't blow up awfully. And yeah, it works. So another great thing about Testground is that it lets you manipulate the network. So it lets you mimic different network conditions. For our test, we're focusing on 2 values, latency and jitter. Latency is just a flat amount of time added to every network request, and then jitter is a random amount of time. Right now, our default scenario, I think, is 10 milliseconds latency and 1 millisecond jitter. I think I based that off a ping to a server that was pretty close by. And jitter is actually a very important thing, because it allows messages to be received in different orders. We've actually discovered a lot of bugs around messages arriving in unexpected order and causing things to go wrong. So it's really good for battle testing our framework. So yeah, what does it look like if we try to do really slow internet? This is just a run where latency of a second, jitter of 100 milliseconds. And you see our software doesn't perform as well under those conditions, but it still functions, and payments are still going through, which is great. We can also look at a case of unreliable internet, or where there's just a lot of jitter. So this is just 1 second, up to 1 second of jitter. You see much better than the 1 second latency, but still not amazing. But it's really reassuring that we can run this test and have all these messages being reordered and still see everything succeed. And then I guess I also wanted to throw in the super nice case where we just remove any network delays, and yeah, things are super fast in that case, which is not too surprising. But it's also nice to look at the case where there's not too much network overhead, and it's mostly our framework, and that will let us figure out what parts of our framework we can optimize. Contributing back. So we've submitted 2 pull requests back to the Testground repo. One was support for M1 Max, which is great because that's what I use. And another is allows you to start up an additional Docker container when you run the test. This has been really useful for us because we can start up our little blockchain instance and use that. And can't take credit for any of this, though, because both these PRs were actually written by Hannah Howard. We were just able to kind of push them over the finish line. What's next? Well, I think the next thing we want to look at is running Testground in a distributed setup. That's something it supports. You can spin up AWS instances in different regions and have them all and run this. You can run a very large scale test. We really want to start performance tuning our framework. We've just started getting these numbers, so now it's time to start making them lower. We want to look at testing the unhappy path when we support that in our code. What we would really love to do is actually have a Testground test going where we just pick a random instance and kill it, and then our framework should allow for everyone to recover from that. And like George mentioned, we also want to run a Testground test with FVM, and we did have that working, like George said, and we will soon, I'm sure. Yeah, and that's it for me. Any questions?
So I was wondering if you could walk me through kind of the security in the off-chain element, the green box that was in the previous conversation, the virtual channel. And so what was the design choice for doing that? The things that are coming to my mind are, why move that off-chain when, would it be more trusted to be on-chain? Did you make a green box just because for the purposes of the presentation to abstract it? Or is that code proprietary, and like how do you invoke trust and security with that?
Yeah, so George is probably better placed to talk about this, but I can try to give it a little go. Yeah, so first of all, I think all our code is open source. None is proprietary. The big thing about keeping things off-chain means you don't have to deal with like the delay and latency of dealing with the blockchain. So instead of like trying to send a payment on the blockchain in 30 seconds or whatever the block time is, we're able to get it down to like 100 milliseconds. So that's why we've moved that code off chains for performance.
Okay, so that makes good sense. I appreciate that. So the code's open source. Would you at some point consider like, hey, maybe there's a subnet of a subnet that can run at the millisecond speeds and it would migrate there, or is that not on the roadmap?
Yeah, I'm not sure if we've looked into that yet, but I think it's something we'd definitely be open to exploring, and yeah, maybe we could chat about it later.
Cool. Thank you.
Thanks.
When you showcase the multi-hop protocol or multi-hop function, does that multi-hop allow you to multi-hop between different currencies and assets, or is that just within hubs within the virtual channels that you've created?
Yeah, so I think the strength, let me see if I can bring it up here, of the multi-hop is it lets you basically join different hub networks. So if you're only interacting with this one hub, you would only be able to, in a single hop world, you can only open payment channels with other people who are interacting with this hub. In the multi-hop world, even though the retrieval provider is using a different hub, just because these hubs have a ledger channel, you can make a payment.